This is week 5 of an 8-week summer independent research project at Colorado State University. I'm Dan Rayberg. The course number is CS498, and the topic I'm exploring is collision detection, which is a subset of computational geometry. The goal of this research is to formulate a parallel algorithm for collision detection. There are several caveats with this. Notably, I will primarily be comparing against Gjk as a serial collision detection algorithm, and that's because Gjk is a prominent algorithm when it comes to continuous collision detections as opposed to discrete collision detections. Gjk has also been chosen because it's a leading standard in industry for continuous collision detection. It has been revised to work a little bit better with floating point error, and there has even been a version that refitted it into the discretized collision detection problem. In devising a parallel algorithm for collision detection, it seemed like a good place to start with just trying to find the distance between two convex polyhedra. So Gjk is the most comparable algorithm for this. Now, it also deals with continuous collision detection more so than discretized collision detection. This is also a useful feature because something we could exploit if we look at the approach of two bodies that are about to collide is actually trying to find out if they do collide and where and when they do collide. To try to summarize how Gjk works, it finds the closest point between two convex polyhedra by using the Minkowski sum. Now, it's actually the Minkowski difference, but the basic idea with this geometric transformation is to take all of the vertices on one convex polyhedra and add them to every vertex of another convex polyhedra, which should then yield a new convex shape. But because we're actually subtracting vertices from one shape into another, we get a reduced volume for that shape. Moreover, what we can do is check the closest point of this new Minkowski shape in our configuration space, check its distance to the origin, which is the shortest distance between these two shapes. In the case of a collision, what the Boolean Gjk algorithm does is it exploits just searching in Voronoi regions to be a little bit faster, and all it's looking for is whether or not the zero vector at the origin of our configuration space is contained within our new shape formed from the Minkowski difference. Just to re-emphasize, the other algorithms that we could be using primarily focus on just true or false intersection cases, and we really do want to try to find the closest distance between objects, primarily because we could use this in a computational physics setting as well. Knowing this algorithm might be used for computational physics helps outline what sort of choices might be made about the distance testing. The computational physics idea is essentially that we have rigid bodies at the start of a frame. We integrate time to start causing motion with those rigid bodies. Then we would have a collision detection phase to see if any violations occurred from the motion of these bodies, and that if there were any violations, we might have to apply some Lagrangian mechanics to fix these errors. In this research, there was a conscious decision to consider the space of computational physics with the use of collision detection algorithms. This choice was made because it seemed to help outline what new useful applications could exist from a parallel algorithm for collision detection. That is, rather than repurposing things like GJK to find the time of intersection, we could consider how this could be inherently built into an algorithm. To explore how this could be built into the algorithm, it was useful to see what some predominant methods of continuous collision detection involved. And the primary focus ended up being between speculative contacts and time of solving, both of these using the Gilbert, Johnson, and Curti distance algorithm. With continuous collision detection, the primary goal on a per frame basis is to see if we can find a contact point to add into a contact manifold for which the Lagrangian mechanics system is solving contact constraints for. The speculative contact method and the time of solving method go about different means of deciding what the new contact point to add would be. The speculative contact method is strictly a non-iterative method in the sense that there are no sub-iterations that happen between the frame start and frame end to try to find a new contact point. Instead, we look at the integration of motion with a shape, and we see if its conservative bounding volume intersects with any other shapes in the scene. And if it does, we just decide that the contact point that we're going to add into the contact manifold is the point returned from GJK at the frame start location. Now, this does have a problem. It can be wildly off because within that conservative bounding box, the object might not have actually hit the second shape. So we might end up adding a contact point into our manifold which doesn't actually represent any practical constraint to solve. So we end up with a kind of ghost collision that ends up being solved. However, it is really fast because we don't have to iterate over the problem several times. We just use GJK once in the event that the broad collision is found to have occurred. By contrast, the time of solving method is an iterative method. Notably, we can use Newton or the Newton-Raphson bisection root finding method to determine a more accurate contact point. So we start in a very similar way. We kind of have a conservative bounding volume between the start of the frame and the end of the frame to see if a collision might have occurred. However, we'll iterate by bisecting time to see if we actually ever fell within the proximity of what we would call a collision, because again, GJK returns a distance, so we'll have to have some range where we consider a collision to actually be some minimal distance between the two rigid bodies. Now, this method's great because we avoid the ghost collisions. The major downside is it is iterative, and it means it will probably be slower than the speculative contact method. Just to paint the big picture again, when we set up a computational physics problem, we have a frame start and a frame end time, and the primary basis of our logic loop will be to, at the frame start time, integrate some amount of time, some time step, into the velocity of a rigid body, and this will then cause it to be displaced. And after that, we'll just do a collision testing step, and we'll do it in two stages. There will be the broad collision sweep, which is typically a low-cost check for whether or not a collision might have occurred, and usually it's over a bounding volume. And then if that case is true, that is when we revert to a narrow collision check as well. Lastly, if there were any violations found, we use Lagrangian mechanics to resolve those constraints before we actually reach the true end of the frame. Setting in stone the things we're concerned with and using GJK as a focus because we want to try to replicate a continuous collision detection system. The big question is, can we make this narrow collision phase into an embarrassingly parallel problem? We know inherently that GJK is a serial algorithm, but it's incredibly fast because per iteration, it's only looking in the optimal direction. However, it is serial, and getting to the next step in the iteration really does involve solving a previous problem before trying to move forward. However, again, it does it really well, but you can't just isolate these subproblems. You have to do them in sequence if we are going to follow the path to optimize the direction in which we're searching with GJK. As far as the problem we'll try to develop where we can solve a bunch of subproblems independently of one another for an embarrassing parallel problem set, is we're going to heed what GJK already offers, which is a distance between objects. So we're not considering the case where GJK technically fails because the origin is contained in the Minkowski shape. The independent problem set chosen for an embarrassingly parallel environment has been to take the vertices of one shape and project them to the faces of another shape. That is to find the distance of a vertex to every face of another object. Note, if we had one thread per problem here, we could very easily assume that this problem could be solved in parallel without any need to perform any type of sequence or order. There is no serial operation here. We're merely going to find the distance, every distance that is, between a vertex and every face on a second object. To keep these problems pretty straightforward and simple, the only considered shapes for which these distance tests will be performed will be on a simplex. So we have points, lines, triangles, and tetrahedron. With this information, we can start with the ideal scenario, which is to have an incident object and a reference edge for which when we do these distance calculations, we always have a projection which results in a valid distance between the two objects. So using the example of this triangle and this box, and specifically one vertex of the triangle, we can see that we, per vertex, have 4 problems to solve, which is a distance calculation to each of the edges of the box. We also want to make sure that our distance projections are valid, and we can essentially find out whether or not they're useful by just taking a dot product with the edge's surface normal vector, and if it's negative, we know that our point is on the wrong side of a face to be considered a valid distance projection. Of course, when we've settled down on valid distance projections, we need to be able to somehow ensure mutual exclusion to store that value for the given shape. For instance, there might only be one valid distance per projection per vertex on this triangle, but we want to make sure that we're storing the shortest distance since the scope of the problem really is the shortest distance between the two shapes. So we could do that by using atomic operations to store a distance value. And every time we find a valid distance, we'll enter a while loop where we exchange our valid distance value with whatever's currently in the atomic container. Now, the exchange operation will return the previous value, and so we'll do a comparison in the while loop. In case the value returned is less than the value we fed in, well, we know that there was already a shorter distance being held by that atomic variable. So we'll need to try to swap it back in. And this type of compare exchange is not too uncommon. It's not the fastest operation that could happen, but it is a working solution to ensure that we store only the shortest distance after we've solved all of the problems between all the vertices in parallel. Before demonstrating the ideal case in action, it's worth reflecting on the space of problems we're in within the realm of continuous collision detections and what we might gain by making all of these independent problems be solvable in parallel. Firstly, we keep the benefit of speculative context in that we're not actually working on an iterative problem if we have one thread per problem to be solved. And secondly, we can gain the benefit we got from time of intersection solving, which is we get the true contact point between two bodies. Of course, the caveat with true is that we're dealing with floating point arithmetic, so there's going to be some epsilon of error that we're always going to be concerned with due to truncation. But we can solve the time of problem by not just stopping at the distance, but by dividing the distance by the relative normal velocity of each vertex. So instead of just storing the shortest distance between vertices and faces, we would actually be storing the shortest time of intersection to be able to get the time at which two bodies were about to collide. To verify this ideal scenario works, I built a project in Blender with two triangles. The top one would be the incident object and the bottom the reference object. In particular, in this test, we're only testing the one vertex on the far right side of the incident object, and it will be projected down to the plane for which the reference triangle exists on. The incident object has two keyframes to allow motion. Between the keyframes, the motion is linearly interpolated just to ensure that we're recognizing this as a linear problem being solved for a computational physics setting, that is from the frame start time to the frame end time, assuming that there's constant change in motion from the start to the end time. From here, I created a script in Blender. Blender is based in Python, so the script is just in Python. And it does a distance projection, a normal point-to-plane projection test of the endpoint of the incident object to the plane that the reference object exists on. And then it divides that by the quantity of the velocity that is along the same direction of that plane. The script will then output a file storing some of this information to be looked at again later. However, for demonstrative purposes, we can go ahead and use the time of intersection we're finding to set ourselves to a different frame so we can see approximately where the instant object should be colliding with the reference object when we rerun this script. Now when we rerun the script, we'll see the frame approximately at which the intersection occurred. And this looks pretty good. This looks about like what we would expect. If we switch over to the solid form, we can see a little bit better that there doesn't seem to be an intersection that exists at that frame. We can very quickly see why this is the ideal scenario, though, if we just shift the reference triangle a little bit. If we just manually move through the frames, if we just scrub through them, you'll see that we're never actually going to have a valid contact point between the end of the instant object anymore. Instead, we're going to be dealing with a situation of two edge segments intersecting one another, which would be the next most convex part of the feature set for 3D objects. So we now have a complicated situation to try to solve. If we examine this in the 2D case, it looks a little bit more simple though. Let's just consider that we have a vertex that's being projected to a plane, but it has a velocity for which, once it makes it to that plane, it will be outside of the region of the face that it was projected to. Well, we can, and as you can see in the 2D case, just change which object we refer to as the incident object and which one is the reference. So suddenly we can instead consider the reference vertex to be moving and it being projected to a face on the incident object. However, this gets a little bit more complicated in 3D space, as we saw before in Blender, because we can have edge-to-edge intersections. However, we can do something similar to the 2D problem if we just build a transform where our forward vector is along the edge segment of the incident object. In doing so, we'll end up collapsing the edge segment of the incident object into a single point, and we can solve 3 different point-to-line intersection tests to figure out which edge segment the incident edge segment is intersecting with first. This scenario does complicate the number of tasks we actually have to perform to find a valid distance between two objects that reside in 3D space. Enough to the point that it is worth considering that this problem could be subdivided for the embarrassingly parallel environment we're working in if we chose to always solve a problem from this collapsed edge to vertex case against the 3 edges of a simplex. So an additional Blender environment was set up specifically to test if this concept of collapsing a point in 3D could be used to solve the edge-to-edge intersection case. So again, we have the incident object as the triangle on top, and the reference object is the triangle on the bottom. And essentially, we're going to collapse the right edge of the incident triangle we see into a single point, and then just test that against the edge segment, the top edge segment on the reference triangle. For this situation, the script written was set up to go ahead and try to use the time of intersection information to reset the incident object. So let's just run it and see how it works. It seems to correctly find a point of intersection between the 2 edge segments. So if we want to, we can verify just through additional tests that this is still working. So we can reorient the reference triangle a bit more, and when we're ready, go ahead and execute the Python script again. Executing it again, it seems like we found a valid time of intersection, as we found a point a configuration in which the instant object is not interpenetrating the reference object, but instead is stopped at a position just before this edge-edge intersection would have occurred. While this method seems to be working so far to catch the edge-edge case, it is worth noting that this is a very simplified scenario. In fact, there is an explicit assumption that actually enables this to work. Notably, the edge segment of the instant object is considered to have constant linear velocity. That is to say, the endpoints aren't moving at different rates, and therefore there's no rotation involved in this problem. Dealing with rotations will involve working around other solutions to this problem. It is also worth mentioning the extent to which angular velocity was explored within this problem. Here again we have a Blender project where we have a reference triangle on the bottom and an incident triangle on the top, and we can see the curved path of the rightmost vertex of the incident triangle. It follows a huge loop, and you can see that that loop does in fact intersect the reference triangle at the bottom. So something we could do if we wanted to try to solve this problem is first find the shortest distance between the vertex and the plane we want to project to, and then sum the linear velocity of this vertex with the linearized angular velocity of this vertex as well, and then divide the distance by the relative normal velocity of this combined angular and linear velocity. Running a Python script, we can see how well using the linearized angular velocity with the normal linear velocity works in this sort of problem. And it looks like we found a valid time of. You can see that this is floating away from the surface, so it's not perfect. But it's also actually worth noting why this isn't perfect. When we linearize in this particular scenario the angular velocity of the incident object, we're actually going to have a massive quantity of downward motion exclusively, just given the path that this vertex is following. So we only actually happen to find a correct solution here because the reference triangle, the plane it exists on, its normal vector is mostly pointing up. So we can see if we rerun this script after rotating the reference plane so that it's facing more of the green axis, we no longer get a valid time of solution. In fact, we're probably not between 0 and 1 in our time of intersection evaluation at all. So the configuration of the incident object isn't even along the path it was traveling on. This was explored mostly to see how extreme we could get in terms of not solving a root finding problem for a very complicated path that a vertex is traveling on. However, what we can realize with this is despite having a mostly downward velocity from linearizing the angular velocity, we're in a situation where our computational physics system that we described is probably not going to work correctly. Notably, if we have a conservative bounding volume representing the path traveled at the start of the frame and the end of the frame, then you'd actually see that our bounding volume would never even intersect the reference object, which means that the broad phase collision detection system would say that there was no collision that occurred in this case. So we don't actually need to worry about trying to solve overly complicated problems in this system. We can really worry about linear problems. I have an older test environment that I've been repurposing for this specific research The old test environment includes the GJK implementation I will be using to do a performance test near the end of this project. This environment also includes the means of parallel dispatching that I'll be using in this experiment. Notably, I'll be managing a thread pool inside C++ to dispatch threads when work is available. As such, this means having a series of classes and functions built out for dealing with the linear algebra operations we'll be performing, so having a vector class and various operations for the vector, either between vectors or more complicated things like cross products and dot products. And for GJK in particular, we have closest points that are analyzed through barycentric coordinates. This is a shape class that we'll be using with our GJK implementation. Aside from that, we have the temp class, which is managing changes to a thread when we create our thread pool. And we'll also be detaching it to ensure that we have daemon threads running to try to maximize parallelism. We have the T count of 15. For this specific system, we have 16 threads. So we're going to have 15 worker threads and keep the last thread, the parent thread, working on its own. We don't want to try to declare 16 working threads because we want to try to avoid performance hits from context switches that might happen. Within this environment, I went ahead and wrote a function for the worker threads. This is the basic idea behind how the worker threads execute. They'll exist within a while loop to preserve the active thread pool until it's time to terminate the program, in which case we'll make sure that they escape this while loop that's held by whether or not the end dispatch is true. There will be a starting line for which the threads accrue at until the parent thread releases them. Once released, they will figure out of n problems which of those n problems they'll be working on, and they'll just enter a basic for loop to perform each of those tasks. Of course, this is because this isn't an ideal, embarrassingly parallel environment. We're only limited to 15 threads here, so it's very likely in large problem sets we're going to have to have one thread working on many problems. The problem setup in here is not the true ideal case of projection. It was an initial test to see about how long it takes, given n problems, to do n point-to-plane projections, and then also to be divide that distance by relative normal velocity to yield a TOI. Now, note that we're also just storing all of the time of intersections here in a large array, as opposed to actually testing the performance of a swap exchange while loop that compares whether or not this result is actually less than the previous result stored in an atomic variable. You can see the means of synchronizing threads from this thread pool. The threads will state at the starting line. Once they make it through the task they're working on, they're actually going to be incrementing a counter, much like you see at the top here. And that counter essentially will be the cue to a thread. A thread will know whether or not it's the last thread to finish something, and if it is, it notifies the parent that just to say, hey, all of the workers are done doing whatever, and then the parent thread can reset the workers from this finish line at the bottom back to the starting line at the top to get ready to be dispatched again for another task. This environment has the vertices, edges, and faces just statically defined for 3 different convex polyhedra. We have a cube, which is the simplest object. We have the convex hole that would encapsulate Suzanne the monkey, as found in Blender. And we also have a sphere built of about 242 vertices as the most complicated object to test in this environment. This environment isn't the primary thing being used for this research, but it has been repurposed because it was a good starting point, and it's where we'll go ahead and gather some basic GJK performance numbers. Testing the most complicated shape first. GJK takes about 13 microseconds to do a distance test between 2 of our spheres. And for the parallel dispatch, the vertex count on the sphere is 242, so we're doing 242 projection to plane tests in parallel. The results of those parallel execution times are also in microseconds, so we can see it's actually performing a lot of point-to-plane projections and calculating a TOI very quickly. Suzanne's convex hole is 66 vertices, and we can see it takes 7 microseconds for GJK. And then the parallel dispatch is doing the 66 vertices instead of 242, though it is worth noting the time of value at the bottom is now incorrect because it was built exclusively for the case of the 242 vertices. A cube takes 6 microseconds and also takes very little time in the parallel dispatch. The last bit of work within the software environment to demonstrate is the revised environment. So this environment is more specific to this research project. There are 2 parallel functions to focus on in this task, though. We have the point projection to planes, and then we evaluate a time of intersection by dividing that by the velocity of the vertex in each of those tests. But then there's also a separate parallel function for gathering relevant faces from the reference object. This is an important idea to mention because when it comes to parallel algorithms, consider something like the scan algorithm that can be used for prefix sums. You don't actually complete the task of performing prefix sums in one dispatch of a thread pool. You end up having several batches of dispatches occur until the problem is solved. So similarly, in the development of this algorithm, we could consider the fact that we don't necessarily need to test every vertex against every face of the reference object. In particular, if we're only concerned with valid projections, that is to say, projections in which a vertex is actually heading towards the surface normal of a face on the reference object, well, then we can use one of our parallel dispatches to try to only find the relevant faces to test against. This will reduce the problem size for the actual projection tests and should help the overall performance of this parallel algorithm. Now, it is worth mentioning that the values we're going to demonstrate from executing this software for the 3 different shapes, the sphere, Suzanne's convex hole, and a cube, we will actually be looking at the worst case scenario too, which again should not be plausible. The worst case scenario being that we will test each vertex against all of the faces of the corresponding object. On top of that, we'll have separate dispatches where we're also just looking at the ideal situation, which is from running the face gathering dispatch first, then seeing how long it takes to perform those projections using only those faces. Starting with the cube, we do a test to see how long it takes to gather relevant faces for this particular shape. That is to say, if the instant and reference object are just cubes. We can see that it took about 1 microsecond for each of the dispatches for this test. Then using the faces that we've gathered, we can do the time of intersection test to see how long that takes. Which takes about 1 microsecond again. And the third test with the cube is to see the worst case scenario, in which we're testing all the vertices against all the faces of a cube. But still, it's pretty fast. It finishes in about 1 to 2 microseconds. We repeat the process for Suzanne's convex hull, and we'll see that it does actually incur a little bit more time to execute, but that makes sense because the problem size is greater. So this was the face gathering step, and then we move on to the ideal time of intersection step, in which we use the faces we gathered in the previous dispatch. Again, performance is a little bit worse here because the complexity of the problem has increased in terms of having more items to work on by the threads, but it's still well below the GJK execution for Suzanne. And we can start to see where face gathering is important, because if we just test all the vertices against all the faces, performance is an order of magnitude worse in these previous tests as well as compared to the GJK test. And finally, we repeat the process for the sphere. We start by gathering the faces that are relevant to test, and it takes a little bit longer, but our problem size has increased, so again, that makes sense. Then we test against those faces for a time of intersection. Again, we'll see that as the problem set has increased in size, performance takes longer. But what is most noteworthy here is how much we actually gain in terms of performance by doing a gather of the relevant faces in one thread dispatch. We can see 2 orders of magnitude worse performance overall when testing all the vertices against all the faces of this sphere. The remainder of time spent researching this topic will be verifying that we have all of our bases covered when it comes to finding the shortest distance between convex polyhedra. There are some lingering questions in case there is time to explore these topics further, such as whether or not in this space, if we're actually limited to having convex polyhedra, or if any closed form geometric primitive will work so long as it's built by simplices, that is, points, lines, triangles, and tetrahedron. Of course, we're not even concerned in the tetrahedron case because we're only trying to solve problems that involve the surfaces of objects, again, the wholes of objects. Aside from that lingering question, problems we will examine more closely as we verify that this process of collision detection is working and is logically complete, is wondering whether or not this linear assumption is sufficient for computational physics. That is to say, this model fits a Verlet integration scheme a little bit better than some other forms of time integration. Secondly, we want to know if this really is faster than doing the root finding in the GJK case. Now, GJK has a benefit in that you can actually use the previous solution to warm start the next use of GJK. So GJK might still win out when it comes to doing root finding, because it might only have one iteration to do. That is, it could run in constant time on subsequent executions when doing bisection root finding. And lastly, there's still a question of if the GJK root finding method is ultimately faster than this parallel system, and though this parallel algorithm would scale with more cores and threads available, wondering if we could actually take our linear assumptions to instead parallelize GJK's root finding method. Moving the GJK method into a parallel execution would essentially mean divvying up the path traveled of an object into discrete segments for which one thread will work on that one problem set. A useful note in terms of doing that, one of the benefits that the parallel algorithm currently being worked on is if its time of method works correctly, then it will ensure that we're always finding the first time of intersection. GJK can, in failing scenarios, depending on the angular velocity of the bodies involved, find a valid time of intersection between two objects using Newton's method. However, because we're doing it by bisecting time, we might actually be finding a different intersection that isn't the first intersection. So something that would be unique in terms of still using GJK in a root finding manner, but in parallel, is we'd be ensuring that for each discrete interval from the frame start time to the frame end time, we could actually find the true first time of intersection, which subsequently might be able to improve upon some of the errors caused by performing root finding on a single thread in a serial fashion.